This is Lab 3, Black Hole. First, we will go over the table of contents, and then the first is going to be the introduction, which starts with the purpose of analyzing the star's motion to determine the mass of the black hole for part 1, and for part 2 is simulating the motion of a spaceship and planet around a black hole. And then we're going to be assuming that there's no external forces acting on the spaceship in part 2 other than the planet and the black hole, and for part 1 we're going to assume that there's no external forces acting on the star other than the black hole. And the key concept is going to be the law of gravitation, the equation shown here, and we can actually solve for the mass of the black hole as shown on the right for part 1, and then next is Newton's second law, which shows the relationships between the force and momentum, and then we have the velocity and position update formulas. And the result preview for part 1 will be a star orbiting the black hole, and for part 2 it will be the spaceship leaving the planet and traveling towards the black hole but not getting pulled in, but the planet will continue to orbit. Now for the experiment, first is the free body diagrams for part 1 on the left and part 2 on the right. For part 1, the system is going to be the star and the surroundings, everything else, the black hole included. And then the star is going to be pulled in to the black hole from the force of gravity of the black hole, which is the only force acting on it. And for part 2, the system is going to be the spaceship, and the surroundings is going to be everything, including the planet, black hole, and everything else. And there are two forces acting on the spaceship, the gravitational force from the black hole on the spaceship and the gravitational force from the planet on the spaceship. There's also two forces acting on the planet, the gravitational force from the black hole on the planet, as well as the gravitational force from the spaceship on the planet. And for part 1, the initial conditions are going to be on the left and as shown over there, and then on the right is going to be the iteration. First, I started out by finding the momentum of the star, and then I found the change in momentum, and I related that to the net force through Newton's second law, and then we found the parallel and perpendicular components of momentum, and at the bottom I found the mass of the black hole by using the formula, which we solved from the law of gravitation before. And then we use that mass that we calculated from there in part 2 in the initial conditions for BH.m, the mass of the black hole. And then on the right is our iteration. I first started by finding the forces. So for the forces on the planet, I used the law of gravitation to find both of the forces, and then I added them up to find the net force. And I did the same thing for the spaceship, and then I used the velocity and position update formulas to update the motion of both the planet and the spaceship. Now onto the data analysis. This would be the part 1 data analysis of the star orbiting around the black hole. And I calculated the average black hole mass to be 1.6230 times 10 to the 34 kilograms. And this is which I used the mass calculated from before in this one, and the initial velocity that I was able to put in was as shown. And the closest distance it got to the black hole was 1.74 times 10 to the 9 meters, and the trajectory came out as shown over here. Now for the discussion for part 1, we saw that the star moved in an elliptical orbit around the black hole, and as the star got closer to the black hole, the force of gravity on the star increased and it sped up, and we're able to estimate the mass of the black hole from that simulation of the star's orbit. And some potential errors could be rounding of the initial conditions or any step along the way, also not accounting for any other external forces other than the black hole that may be prevalent from any objects that we didn't account for. And for part 2, we saw the spaceship leave the planet and go towards the black hole, but it flew past its orbit. And we also saw that the planet continued to orbit the black hole, and then we found this to be the initial velocity of the spaceship, so it was not able to be sucked into the black hole. And potential rounding errors could be rounding of the initial conditions, such as the black hole's mass, which I had to manually put in, so there was rounding that could have been messed up there, and any intermediate step. And not accounting for any other external forces other than the planet or the black hole may result in different answers in the end. And so on to the further questions. For the first question, how does the net force and its parallel and perpendicular components differ from the rate of change of momentum and its parallel and perpendicular components? They don't differ, they are equivalent. This is because of Newton's second law, which states that force is equal to the change in momentum over the change in time, as shown by these equations. Each of their corresponding parallel and perpendicular parts will be equal to each other because they are equivalent quantities. And now for the last question, the initial velocity of the spaceship for it to be able to get into the orbit around the black hole was this right here, -2 times 10 to the 6 meters per second, and 1.05 times 10 to the 7 meters per second. I needed a more vertical liftoff trajectory to be able to get the orbit as shown on the right. So I had to reduce the velocity in the x direction and increase the velocity in the y direction. And that's it. That's the lab. Thank you.